Hello everyone and welcome to my talk on Crafty, an efficient HTM-compatible method for persistent transactions. Let's first look at what persistent transactions are. Persistent transactions are a programming model in which a code region is executed and the data used within the region is persistent, meaning that it will survive power failures. And the region is executed atomically, meaning that should a power failure occur, the region will appear to have executed completely or not at all. And concurrent transactions are isolated from each other. To provide isolation, we want to use hardware transactional memory, which is an efficient concurrency control implementation within the hardware itself. And for the persistency, we want to use non-volatile memory. Non-volatile memory, such as Intel Optane DC memory, is a new class of memory that is persistent, meaning that it does not lose data on power failure. It's also byte addressable and it can be accessed with regular reads and writes. One issue with non-volatile memory, however, is that not all of our memory hierarchy is persistent. In current designs, the CPU cache is not persistent, which is important because when and in what order data is written back from the CPU cache is unpredictable, which makes it hard to write persistent memory programs. Persist operations help us control when data gets written back from the cache. However, that brings me to my next point. Hardware transactional memory and non-volatile memory are incompatible because hardware transactional memory prohibits data from being written back during a transaction, which means that persist operations are not allowed. Luckily, there are ways to get around this limitation, which we will talk about shortly. During this talk, I will be talking about the prior methods for persistent transactions and their drawbacks, and then I will present our work, non-destructive undo logging, which overcomes the drawbacks of prior methods, and then I will present our work, Crafty, which uses non-destructive undo logging to implement persistent transactions. And finally, we will look at some experiments for evaluation. Let's start with prior methods. One method that has been proposed is undo logging. This is a simple method where at each write, a undo log is created. However, this is a destructive logging method, meaning that at each write we need a persist operation, which is very expensive. Additionally, because of those persist operations, it is incompatible with hardware transactional memory. Another method that has been proposed is redo logging, which, in addition to replacing the undo logs with redo logs, also avoids performing the actual writes themselves. Instead, the writes are performed from the redo logs at the end of the persistent transaction. This allows it to avoid the overheads of undo logging. However, since the new values only exist within the redo log, subsequent reads have to search through the log to find these new values, which adds non-trivial overheads. Next, we have the shadow memory methods. These are recently proposed works that create a volatile shadow copy of the entire non-volatile memory. These methods avoid the overheads of undo and redo logging. However, they suffer from scalability bottlenecks as they have to keep shadow memory and non-volatile memory in sync. So in summary, there are two problems that we want to tackle: the limitations of the existing logging methods and the incompatibility between non-volatile memory and hardware transactional memory. Next, let's look at our work, non-destructive undo logging, which overcomes the drawbacks of prior works. Non-destructive undo logging utilizes existing hardware transactional memory to minimize the number of persist operations that are required, and it has very low overhead. Non-destructive undo logging works by executing a code region within a hardware transaction. During the execution, at each write, an undo log is created, and no persist operations are used at this point. Normally, this would be unsafe. However, before the end of the hardware transaction, using these undo logs, all the writes that were performed within the code region are rolled back. This way, at the end, the program memory is unchanged, and the partial modifications that were performed never reached non-volatile memory as the hardware transaction was keeping them from being written back. This also provides efficient concurrency control. Next, Let's look at how Crafty uses non-destructive undo logging to implement persistent transactions. Crafty works in multiple phases, with each phase executed in a separate hardware transaction, which means each persistent transaction will include multiple hardware transactions. And Crafty maintains the atomicity and persistency across all these hardware transactions. Let's start with Crafty's first phase, the log phase. During the log phase, Crafty uses non-destructive undo logging with a small addition. During the rollback, it creates redo logs in volatile memory. Next, Crafty takes these redo logs and enters a redo phase, in which it applies the redo logs within a hardware transaction. One problem here is that the undo and redo phases are executed within separate hardware transactions, which can cause issues with concurrency. To understand that, let's look at the following example. In this example, we have two threads executing persistent transactions. And the problem here is that the redo phase uses redo logs that were generated during the log phase. Should a redo phase of another persistent transaction, for example T2 here, execute between the log and redo phases of a persistent transaction, T1 here, T1's redo phase may see stale values, which can cause issues with isolation. To avoid these issues, Crafty saves the timestamps of the log phases for each thread. These timestamps come from the RDTSC instructions, which are hardware clocks that are synchronized across all cores. Next, during the redo phase, Crafty checks this timestamp against a global timestamp. If the check succeeds, Crafty updates the global timestamp and completes the redo phase. Should the check fail, the redo phase fails. If the redo phase is successful, Crafty can end the persistent transaction. However, if it fails, additional work is required. One important insight here is that the redo phase can fail even when persistent transactions did not actually conflict with each other. To capture such cases, Crafty uses the validate phase. During the validate phase, Crafty re-executes the original program code within the persistent transaction, and during that execution, Crafty checks the values of the undo logs. If the values match, and the number of writes within the region match, then the validate phase is successful, and we are guaranteed that no conflicts happened within persistent transactions and the logs are not stale. However, if they do not match, then the logs are stale and the validate phase fails. If the validate phase succeeds, Crafty can end the persistent transaction. However, if it fails, because we know that the logs are stale, we have to go back to the log phase and get new logs. Note here, however, that both redo and validate phases are completely sufficient on their own to complete a persistent transaction. However, each is suitable for a different kind of workload. The redo phase is good under high contention and low thread counts. On the other hand, the validate phase is good under low contention and high thread counts. By combining both phases, Crafty is able to cover a wide variety of applications. Next, for optimization purposes, if a persistent transaction performs no writes, Crafty can simply complete the persistent transaction without performing the redo or validate phases. Finally, the current design of hardware transactional memory and the design of Crafty itself does not guarantee progress. In order to do that, we implement a single global log fallback. The fallback works similarly to the log and redo phases. However, instead it uses exponential backoff to chop persistent transactions into smaller pieces until they are able to execute, falling back to simple undo logging if necessary. Finally, let's look at the results of some experiments to see how Crafty performs. We perform our experiments on a 16-core Intel Skylake processor with hyper-threading disabled. We use native hardware transactional memory, but we emulate non-volatile memory with a latency of 300 nanoseconds. We evaluate Crafty against NVHTM and DUTM, which are recent shadow memory methods using hardware transactional memory, which we believe are the closest to Crafty in terms of performance. We also evaluate a non-durable configuration where no persistence is performed to act as a baseline. Here we have a micro-benchmark in which a B+tree data structure is manipulated within persistent transactions. In this graph, only inserts are performed on the B+tree. Here, we see that Crafty is able to scale better and outperform NVHTM and DUTM, as NVHTM and DUTM suffer from scalability issues as they have to synchronize their shadow memory and non-volatile memory. Next, we have the vacation benchmark from the stamp benchmark suite. The stamp benchmarks are not persistent memory benchmarks. However, following prior works, we evaluate them by assuming that all shared memory is persistent. Here, the vacation benchmark has been configured to have a low or high level of contention. We see that under low contention, Crafty is able to outperform NVHTM and DUTM, and under high contention, it performs similarly. Next, let's look at the SSEA2 benchmark from the stamp benchmark suite. Here, we also compare Crafty with two configurations of Crafty: Crafty no redo and Crafty no validate. These configurations take out the validation and redo parts of Crafty respectively. Note that these configurations are also completely valid persistent transaction methods. This is one of the few benchmarks where not combining the redo and validate phases actually leads to better performance. As we can see, Crafty no redo performs better than Crafty itself. This is because SSEA2 is a very low contention benchmark, which means that not even trying the redo phase is actually better than attempting the redo phase, failing, and then falling back to the validate phase. Finally, to recap, non-destructive undo logging creates undo logs without modifying program memory, separating logging and persistence. Crafty uses non-destructive undo logging to provide efficient persistent transactions, and it has low overheads for low contention programs. Thank you for listening.